We argued that we expect the Hamiltonian for a free Klein-Gordon field to exhibit the same structure as a harmonic oscillator. Now we are going to explicitly calculate this Hamiltonian. We express it as a space integral of Hamiltonian density, and we obtained its expression from Noether's theorem. We showed that for the Klein-Gordon Lagrangian for a real field, the canonical momentum is just a time derivative of the field itself. And the Klein-Gordon Lagrangian is expressed as function of the time and spatial derivatives. We now would like to express Hamiltonian as function of the A and A dagger operators, and for that we need to recall the expression for phi, the time derivative of phi, and its spatial derivatives. We see that we need square of phi dot, and square of nabla phi. So we need to square these expressions. So we will have terms which will have this product of two of these exponentials, one with k and one with k dash. And we will also have terms with product of this exponential times this exponential, again one with k and one with k dash. And we will have to take the space integral of these terms. So let's write one of them. We recognize the delta function. And we will also have terms which involve exponential with positive frequency times exponential with negative frequencies. We now write the Hamiltonian combining terms in A dagger, A dagger, A dagger, and A dagger A. The A term will involve this integral. We will have a term coming from the phi dot squared, which will involve a minus I omega k times minus I omega k dash. We have a similar term coming from nabla phi squared, which involves an ik times ik dash. And finally an m squared coming from the phi squared term. Because of the delta function, however, we have k dash equal to minus k. So we get minus omega k squared plus m squared, but using the definition for omega k, we see that this term is 0. So there is no A term. We can show similarly that there is no A dagger term either. So we are left with an A dagger term and an A dagger A term. The phi dot squared term gives us a minus I omega k times the I omega k dash. The nabla phi squared will give us an ik times the minus ik dash, and the mass term will also be there. Now the delta function imposes k equal k dash, and we get the same thing for the A dagger A term. So we can kill the integral over k dash thanks to the delta functions. The square root of omega k dash just becomes omega k. So we have 2 omega k in the denominator and 2 omega k squared in the numerator. So we cancel 2 omega k and only 1 omega k is left. We can rearrange this term using the commutation relationship for A and A dagger. We recognize, as expected, expression analog to the harmonic oscillator. In fact, we have an infinite sum of harmonic oscillators because we have one for each momentum k. We see that the integral times a constant gives us an infinite. But this doesn't really matter because it's just a constant. It's infinite, but it's a constant. Therefore, because the energy is defined up to a constant, infinite or not, we can get rid of it if we wish. It's still a bit annoying because it corresponds to the energy of the vacuum, and having the energy of the vacuum being infinite is not very satisfactory. However, we will see that when we have fermions, perhaps this can solve the problem if we have something called supersymmetry.